All right, so for making this graph here, we see it's a square root graph, so we know the shape already is going to be one of those. And then the -2, that is on the inside with x, so we know it moves it in the x direction. Specifically, minus moves it to the right. And then the +3, it's hanging on the end. Therefore, that's moving it up and down. Specifically, it's going to move it up. So we're going to go right 2, up 3, and that's our starting point of our square root graph. And from there, we plot the points the same way as we always would for square roots. So that's going to be over 1 and up 1, over 4 and up 2, and then over 9 and up 3. Now for me, over 9 up 3 is off my graphing grid, so I'm not actually going to plot that formally. But if it fit on your grid, go ahead and plot that one. And then draw the curve through it. Next up now, I would like you to please graph the inverse of the same equation. So graph the inverse, please, on the same set of axes. Now, if you're feeling a little bit stumped about how to approach that, though, let's take a look here. So there's multiple methods that you could actually use to be able to graph the inverse, but perhaps what I would suggest as being your fallback, the one that can always work if everything else fails, is that because we do know some specific points, we can just take the coordinates of one of those points, like our first point was at 2, 3, and we can swap the x and y of those points. Because remember, inverse means to swap the x and y. So if I swap x and y of that coordinate pair, I end up with 3, 2. And so I can go ahead and plot the point then at 3, 2. And even if I don't know how to make that graph any other way, I can do the exact same thing for the other points in the original. Write out their coordinates and swap x and y. Although taking the individual coordinates and swapping the x and y isn't the only way you can go about doing it. Another way that you could go about doing it is that you may recall that the inverse graph is the original graph, except it is reflected across the line y equals x. And so I can actually draw in that line at y equals x there, and then reflect each of the points over. So like I could use the same thing to get that point that I just found, because to reflect it across a line, you're going to go perpendicular into the reflection line. Basically, you go perpendicular into your mirror. So you notice that going from my original here, I went through about half of the box diagonally. So I'm going to go through half the box diagonally to get to the other one. That's how I can know where that point is. I can do the same thing for all of those. So I go perpendicular to the line. Again, I happen to go through half the box this time, so I'm going to go through half the box again this time. And then that's going to drop me off here. The same point that, yes, you would have gotten if you just took the x and y coordinates and swapped the x and y. And then we do the same thing with this last one, which also happens to be just half a box diagonally. And so I go the same distance on the other side, plot the point, and I now have all 3 points of my inverse. When drawing in the curve, though, through those, the curve will be the same shape, because the original and the inverse should always have the exact same shape. And so since I know that the original had this shape, I know it will be the same. It'll just be turned the other direction because it's being flipped over. And so make sure you have that one drawn nicely. That can often help as a way to know how to actually draw that curve in, because otherwise we might just think, well, I only got a few points, I don't know what the graph looks like, and we might get a little bit off track there. And so this helps us to make our graph a little bit neater that way. All right, so we saw how we can get the inverse graph. But notice, I didn't even need the equation for it. I made that inverse graph only from the original graph. And that's one of the skills we need to have from this, is just being able to go from that original. All right, now, looking at those 2 graphs, I want us to figure out the domain and range. All right, so for the original, we're starting with our domain. First thing I want you to note here is that the domain is not all real numbers, because it has a hard stop. It only goes over this far, and then we're going to the right from there. And so our starting x value then is 2. And since they're getting bigger, you would say x is greater than or equal to 2. Next up is the range. And again, not all real numbers this time because it's only going down this far. And then we're going up from there, looking at the original graph there. And so you notice that my starting y value is 3, and we're going up from there, so it's going to be y is greater than or equal to 3. Now if I wanted to, I could do the exact same thing to find the domain and range of the inverse. I could look at my graph and I could get it that way, but I'm going to try to start breaking us out of that and utilizing more what we already have written down, because it's going to be faster, and as you're going to see later on today, it's actually going to be potentially more accurate as well. Remember that the inverse's domain comes from the range of the original. So I know then that my domain of my inverse still must be a greater than or equal to 3. Just remember, we are swapping x and y, so it's going to be x is greater than or equal to 3. Remember, domain is talking about x values, so yes, domain will still be talking about x values even for the inverse. All right, and then for my range, well, that comes from the original's domain. And so in that case, it's going to be that y is greater than or equal to 2. And yes, you could have gotten those same piece of information just by looking at the graph up here. But we are able to get it just from knowing the original domain and range. And that's going to be useful information as we go forward. So make sure you have those written down correctly there. All right, so I now do want to take a look at how we could actually find that inverse equation, though, just kind of give us a fully rounded out picture. So we have our original equation. Please write it down and then show the algebra. How would you find the inverse equation? Now, it's possible that you're a little thrown off at the start about what to do first. So let's make sure that we understand. How do we know what we start with? Well, first of all, it's asking for the inverse. Whenever you see that word inverse, I want you thinking swap x and y, because that's what the inverse is telling us. At its most fundamental level, that is the essential learning about an inverse, is that all it does is swap x and y. Although you might get a little thrown off in this particular case because there is no y. Well, what's playing the role of y here? Yeah, the g of x. And so if it helps you just to keep track of it, feel free to write it first as y equals the exact same thing. Now this isn't actually the inverse yet. We're just making it a little bit easier to go to the inverse. But I'm just pointing out g of x is the same as y. Because if I am going to now swap the x and y, I now can see exactly what that means. So to write my inverse equation, I'm going to go x equals the square root of y minus 2 plus 3. So notice, we literally switched the x and the y. Nothing else about our equation changed. Now that we're here, solve it for y. Because while this technically is the inverse, we always do want our inverse written as a y equals equation. So please finish solving it out for y. I don't know if I'm going to be solving the square root equation for y here. But it looks like the first thing I'd want to do is get rid of this plus 3 that's hanging on the end, because I got to get the square root by itself. So I'm going to subtract 3 from both sides first. So that gives me x minus 3 equals the square root of y minus 2. Now that I have the square root by itself, now I can get rid of the square root. And of course, in order to undo a square root, we square both sides. So on the left side then, that's just going to become x minus 3 squared. And on the right side, squaring the square root cancels out the square root. So we're left with whatever was on the inside, the y minus 2. Now a little side note here. I saw a few of you on yesterday's assignment where you really wanted to multiply this out. And technically you can multiply it out, but it does not give you x squared minus 9. It also does not give you x squared plus 9. Because remember, if I'm going to be actually doing x minus 3 squared, I would actually have to do it as x minus 3 times itself. And then I have to multiply everything in the first parentheses by everything in the second parentheses. If you did that, it would give you x squared minus 6x plus 9. But the good news is, you don't even have to do that. In fact, it's preferable to leave it as x minus 3 squared. It's going to make it a lot easier if we go and think about the graph that way. All right, so Next up, last thing actually, in order to get the y by itself, we're going to go ahead and just add the 2 to both sides. And so then we are going to end up with our x minus 3 squared plus 2 equal to the y. And this is very good. This is a good inverse equation. Although it's not quite perfect, I could actually tweak that just a little bit here at the end to make it just a little bit nicer looking. Because remember, our original up here was g of x equals. The original was not y equals. So, I mean, it'd be great if I could put my final answer here in terms of g instead of y. Now, do you remember from yesterday how I write the inverse of g of x? Do you remember what that notation looks like? Good, yeah. That means g to the power of negative 1 of x, or at least that's how we write it. Remember, that's not technically an exponent of negative 1. It actually means inverse, but it goes in the same way as to the power of negative 1. All right, and so then that equals the exact same thing, the x minus 3 squared plus 2. And that's an ideal then for our inverse. Now, if we then took this equation, if I just graphed it though, I wouldn't end up with this graph over here. If I graph that, I would also have this other side. So how do I know that it's only supposed to be that one side when I write this inverse equation? Well, remember earlier when we found the domain and ranges? That's actually why. Because domain and range up to this point have always been descriptors of our graphs. We've always just looked at the graph and we've said, this is where I see the x's and this is where I see the y's. But domain and range actually can be used beyond that. You can actually use domain and range to restrict a graph or any other type of equation to certain values. In this case, you remember what our domain was? You hopefully remember having written it down. Earlier, we found that the domain of this inverse equation was supposed to be x is greater than or equal to 3. Notice, if I add this line of work to my equation here, I then know where to make that graph, because it tells me, yes, make that graph of that whole equation, except only plot the points where x is greater than or equal to 3. So it's telling you, leave off the left side. And so this would actually be our final inverse equation. There's this one little layer. This is actually the only new learning we're getting today. Everything else is just practicing what we did yesterday. But this would be our actual inverse. Notice it has this domain restriction on it. And yes, we do need to include it. We're now going to go ahead and do 3 last little problems here. 3 practices converting, or actually finding, the inverse from an original. So please write down this equation, and please find the inverse equation. Of course, the first thing we do is we swap x and y, and so you'll notice that gives us this equation. And then once we're there, you're solving that equation for y. And so if I'm going to solve this for y, first thing I want to do is get rid of the plus 6 there. So I'm going to subtract 6 from both sides. So that gives me x minus 6 equals negative 3y. And I just have one last step in order to be able to get the y by itself. What am I going to do to both sides here? Am I going to add, subtract, multiply, or divide? We are going to divide. And I ask that question specifically because a lot of people will see that minus 3 there, and they will internalize that as subtract 3. And they'll try to add 3 to both sides, but that doesn't work because this is negative 3 times y, which is why we then have to divide both sides by the negative 3, which if we just wrote it out as rough as we can, this is what we'd be left with, x minus 6 all over negative 3. But I really don't want to leave it there because, like, if I was trying to graph this, that'd be rather challenging to be able to graph. It's not a form that we're used to seeing. And so, let's put this into more of a typical form. If I'm going to be taking this and dividing everything on the top by negative 3, that actually means I'm dividing each of the terms on the top by negative 3. So if I just do that, that would give me x over negative 3 plus 2 equals y. And even that's better. I now know that I'd be starting up 2 if I were graphing it, but it's still not great because how do I deal with x over negative 3? Well, that is the same as negative 1/3 times x plus 2 equals y. This form now is more comfortable for us to be able to actually graph this if I am having to graph such a problem. Because I can now look at this and say, okay, great, well the slope is negative 1/3 and the y-intercept is 2, and I can graph from there. So then, based off of this, I want you to be able to think about what the domain and range would look like. Now, I'm not going to make you graph these. You should be able to come up with the domain and range of this particular one without graphing them. So take a moment, visualize it, and think about what you would expect them to be. And so the reason why I can do this one, especially without actually making the graph, is because I know what the shape of this would be. If I graph that, it would just be a line. And what is the domain of a line? All real numbers. And the range of a line is all real numbers. And since the domain and range are both all real numbers of the original, the domain and range of our inverse are also both all real numbers. Do that process again, please. Find the inverse of this one. Of course, you start by switching x and y. Notice the operations stay in the same place, though. The squared is still on the right side. The squared did not move with the x, because all I'm doing is swapping the letters. All right, now solve it from here. I'm going to go ahead and move that 9 to the other side. So I'm going to add 9 to both sides. So x plus 9 equals y squared. Now I need to get rid of the squared, so I'm going to take the square root of both sides. Now, if you wrote this, however, there's something slightly missing. What are we missing on this line? Yep, that plus or minus. So remember, if we take the square root ourselves of both sides, we have to remember that plus or minus. Now this is looking really good. One question though, can I then turn this into plus or minus the square root of x plus 3 or something like that? No, we can't. The reason is because of this plus. Because it's adding on the inside, not multiplying, we can't just take the square root of each term individually. So no, that would not work that way. You have to leave it written like this. And so once again, I want to talk domain and range for these. And we can still do this one even without actually having to draw the whole graph out too. Although we will visualize it at least. Because if you were going to graph this, what would the shape be? Yeah, it's that U-shaped graph. What do we call that graph?
Parabola.
Yep, nice. It's a parabola. Yes, we got to get that technical language down a little bit. So you'll notice that since it's a parabola, we do know what the domain is. Because a parabola goes forever left and forever right. So the domain is all real numbers. The range, however, is not all real numbers. So we need to figure out what our starting y value is. Well, that's going to be however far down it goes. How low did this graph go? That negative 9 on the end shifted it down 9. So yes, that is down at negative 9. So that's why we would say that y starts at negative 9. And since it's a positive x squared, it's going up from there. So we'd say y is greater than or equal to negative 9. And now I can find the domain and range. And I don't even have to picture the graph of the second one. All I have to do is take the original domain and range and swap them. So my domain then would be that x must be greater than or equal to negative 9, and my range is all real numbers. Now this is a problem that you've never seen before in this particular context. We've done lots of inverses, and we have solved absolute value in the past, but we haven't done the inverse of absolute value in the past. What I'd like to do is see, can you put all those pieces together and figure out how we do the inverse of the absolute value then. Now, one trend that I will sometimes see among students is that I'll see people say, well, I don't know how to get rid of the absolute value, so I don't know how to do it. And this is what they've written on their paper for the whole problem. Really? I'm pretty sure we know more than that. Like, what's the first step in finding the inverse? Swap x and y. So we could do that. Even if you don't know how to do the whole thing, you can start it. That step of mentally saying I'll at least get as far as I can through it makes a huge difference in what you can and cannot actually solve in reality. All right, I'm still not sure how to get rid of the absolute value. Okay, but I still can do something else. I can still get rid of that 4 out of that side. So let's add 4 to both sides. So even if you are saying, I don't know how to get rid of the absolute value, you could do that. You could at least get to that point, which is like 80% of the way there. So how do we get rid of the absolute value? Let me take you back to a problem that you did before. What if I give you the absolute value of x equals 5 as a problem? What would x equal in this case? Plus or minus 5. Yep, because the absolute value of 5 is 5, and the absolute value of negative 5 is also 5. So, how do we get rid of the absolute value? It's with a plus or minus. And so, it'll still have the x plus 4 over here, but instead of just x plus 4, we have to make it a plus or minus x plus 4. That's how we get rid of the absolute value. All right, last step. Please take a moment here, figure out what would the domain and range be. All right, now we can again get this domain and range without actually having to make the graph by visualizing it, because we're pretty familiar with this graph. If I graph the absolute value of x minus 4, I know it's a V-shaped graph because it's absolute value. And for all of those absolute value graphs, we found the domain was all real numbers. It goes forever to the left and forever to the right. But the range was not. So I say, well, how far down does it go? And in this case, since it was shifted down 4, it starts down at negative 4. So I'd say for my range, y must be greater than or equal to, because it's going up, negative 4. And based on that, you then can get the domain and range of your inverse, because the domain must be that x is greater than or equal to negative 4, because all I got to do is take the range and make it into my domain, and make the y into an x. And the domain of the original, that becomes my new range. So that's going to be all real numbers. And so we can still figure that out. And that's how you can actually end up with a graph of the inverse here, because if I were graphing the inverse of the absolute value, I'd end up with a V-shaped graph, except it would have to be on its side, because it gets reflected across that line, y equals x. And it's that domain restriction that allows that to happen. Because without the domain being restricted, you'd actually have like this big old X there. That domain restriction gives you just the right side of it.